Okay, wait a second. That is not good. Let's see if this works. All right, I think it does. Well, good morning, everyone. And today we are going to be studying linear algebra. This is a junior level college course. Oh my gosh, my mic was muted the whole time. That is, oh my gosh. Okay. So I'm just going to speed run through this. Basically, you can turn a system of equations into a matrix. There's different row operations you can do on it. That's kind of the basis. All of this is pretty simple. And again, if you perform a row operation from a scalar multiple, and then the final row operation you can have as well. The following is just, so you have, is just Ri. Just gonna leave it like this. Okay, okay. Hopefully, I don't have any more microphone issues for the rest of the stream. That would be really appreciative. For some reason, it keeps on like not recognizing the driver or something stupid. Thankfully, I haven't gotten to like any hard stuff yet. And now let's do the inverse operations, which are pretty simple. So, what's the inverse? Oh, I did not mean to erase this. Well, okay, hold up. Okay, let me rewrite these two real quick. So you have R, I, and okay. So what's the inverse of flipping these two rows? Flipping these two rows back. That's the inverse of that. It's pretty straightforward, simple. What's the inverse of scalar multiplication? Well, scalar division. So it can be worked out as R of this, or better yet, what I recommend more is of this. Okay, so relatively straightforward. And what's the opposite of addition? Well, it's subtraction. So it just becomes R of, would it be R of, okay, yeah, it would. R of I minus C R of J. And also, better yet, you don't even need the scalar multiple. So let me work out a better example actually before I move on to this just so we're clear. Because this, I'd argue these two operations right here are probably going to be the most common when it comes to augmenting a matrix, right? Or when it comes to matrix operations. So let's do an example. R2 minus R of 1. That gives you 2 minus 1, that's 1. Minus 3. And then these top two remain the same. But if we do it again, because you can do this as many times as you want, let's do R of 1 instead. Guess what? The R of 2s are going to remain the same, and you're going to subtract the R of 1 by the R of 2. So, like so. So, pretty simple rudimentary stuff. Don't overthink it. It's not as complicated as you think. And generally, these row operations, once you know them, you should be able to do them pretty consistently because a great deal of this course is about them. And hopefully you don't have to do anything crazy. So now, what we kind of want to do from here is reduce this to row echelon form. I think it's fair to determine that, right? Is that... Should I define row echelon form? Okay, so here's a definition. It's the following: row echelon form. So it's kind of like a state of a matrix, right? So like it's not the simplest form because there's also another form out there that we'll get to eventually. But let's say for a 3 by 3 matrix of say this, let's keep it simple. So what you want to have as well, the bottom left row of this, or no, the bottom left 3 of these to be equal to 0, and then immediately on top of the staircase to be 1s, and then these right here do not matter. They can be anything, including 0 and 1, by the way. So, just a clarification here. Like, for example, the identity matrix has these as all 0s. But the reason why it's called row echelon form is because it, well, looks like a staircase. So how I like to visualize is that the 0s are the inside of the stairs, the 1s are immediately on top, and then anything, whatever else, doesn't matter, sits above that, right? Does that make sense, sort of? I don't know. So, an idea would be, well, to work out the following example we've had here, just like sitting here, begging to be worked on for a while. So, we want to reduce this. So, we want to make these two numbers 0, and then these 3 numbers 1. So, how do we go about that? This first step, I'd say, instinctually is to focus on the leftmost row. And then, oh, we already have 0 here, so we want to make this 0. So actually, no, excuse me, the leftmost column and then the lowermost row, and then work your way up here, here, and here. So kind of a Gaussian elimination tactic would be, well, best thing to do, R2 minus R1, right? So R2 minus R1 would yield you 0, and this would yield you 6. This would also yield you 0, but that's inconsequential. And then this right here also is affected by this row reductions, like even the equals per the augments matrix. So minus 2 minus 1 is just minus 3, 1, 2, minus 7, 8, 0, minus 2, 4. So this is a kind of simple-ish, but let's simplify this further. So what do we want? We want this to become 1. So what do? We 1/3 of R1, so that becomes 1 minus 2 minus 2/3, 4/3. Okay. We're not fully reducing this, so it doesn't matter. This 8 doesn't really matter that much. Well, no, it should be 1 eventually, but I realized we could technically subtract these out, but so then this is 0, 0, minus 7, 8, and then 6, 0. Okay, the rest of the equation is not affected by it. So we can do another operation here. My handwriting is really bad. I'm sorry about that. So let's focus on this minus 7 here. It is a bit trickier to get this to 0, but we can just, let me see here. So then minus 7, we can multiply 6 by 6 over 7, right? So that becomes R3 minus 7 over 6, my bad, R2. Yeah, okay, that works. A bit awkward, but not the worst thing in the world. Trust me when I say I've had to do so much worse than this. So, thankfully, since we're subtracting R2 and not R1, which is less than when possible, when you're subtracting this row, try to make sure this 0 stays as 0. If this 0 does not stay as 0 when you're doing row operations down to row echelon form or reduced row echelon form, you are doing something wrong, okay? There's a much simpler way to, there's a much simpler and faster way to find these, so I just say in general, if you can find the easiest path, do so. Anyway, that would have been bad. So that becomes 0, 0. Okay, 8 plus 0 is 8. And then 2 minus 3 is 21 over 6. That is a bit unconventional. Oh, okay, this actually is working out pretty well. Okay. By the way, don't worry about what the augmented matrix is equal to. This is entirely something else. No, it's just like it's essentially what the matrix is just set equal to, and it's set equal to. We can refer to this as a vector if we really wanted to, but really it's just the solution. The solutions, or not the solution, but what the equation is equal to. The solutions are in again. So then, now, all we have left to do is, well, pretty simple. We have to make this one and make this one, and we are set. So the good thing about making these two things one is all we have to do is just multiply. You don't have to do any fancy add and subtract row operations, which in my opinion are the most tedious. So this is pretty simple. We get 0, 1. I'm running out of space. Okay, let me stand up. Also, it's fine to do this as long as you don't get too lost. You can do multiple row operations at once if you really wanted to save time. Just be careful about what you're doing and like know what you're doing before doing so, because it could confuse you a little bit if you're unsure about things. But yeah, okay, this top row, the row 1, remains the same. 0, 0, and then 1. Okay, and this is fully reduced. Now, what do we do with this? Well, see this equation up here? We kind of want to convert this back into that, right? So let's do that real quick. So that becomes x1 minus 2/3 x2 plus 4/3 x3 equals 1/3. And then this is just x2, which equals, again, it's not always going to be this simple like this. This is just kind of like a, well, actually no. So, hold on a second, actually. The good thing about row reducing, by the way, as well, look at that. You already have two of the solutions. You have x3, which equals 1, and x2, wait, no, x3 does not equal 1. What? Okay. So the good thing about row reduction is that you had this grueling system that would have taken ages and ages, probably not, because there are some things that work out here very well. But if you had a system that was that was a little bit more ridiculous, like say this and like this, it would have taken you a pretty long time to solve for that. But now we've had this in fully reduced form like this. You already have two of the solutions here. So now all you need to do is plug these two solutions into this. And what do you get? 1/2 plus so this is x1 minus plus 2/6, which is just 1/3, and then plus minus 12/6, which is just 2 equals 1/3, and now you subtract. And then, lo and behold, you get x equals 2, and your other solutions you already have from just simply row reducing. So that's x equals 1/3, x equals 1/2, and then x3 equals -3/2. Solutions. And boom, it's a lot simpler than you think. But once you have it down, you have it down. So, right? So you can do this with any size of matrix, theoretically. I've had to do this with, I believe, like some ridiculous, like 7x4, 7x5, something. It's tedious. It's not the most difficult, and it does leave a lot of room for error, but it's, in my opinion, the most effective way to solve for very complicated, long, and overwhelming systems of equations. Right? So that's kind of a cool way to do it. I know some colleges, or not some high schools in other countries teach, when you learn about systems of equations, teach this method, which I'm sure is nice for them. Unfortunately, at least based on my secondary experience, I didn't, and that was a bit unfortunate for me. But we can move on now. Oh, we already did Gaussian elimination. But actually, before we fully move on, there is a bit of a thing we need to do. And that's, well, reduced row echelon form. Reduced row echelon form. So this matrix is in row echelon form, right? So this is in row echelon form. But we can simplify that even further. So let me look at an example of. So yeah. I need to read up on this actually, because for a while I thought fully reduced just meant the bottom, just same as row echelon, but the bottoms are 0. But I don't think that's it quite. So let me just add in some clarity. So you want I need some sort of I need a more defined definition. I need. So, by definition, we have the following properties when it comes to row echelon form, right? So, row echelon form has the following properties. Number one, it has a 0 row applicable at the bottom. So what do I mean by this? Technically speaking, oh shoot. So a 0 row would just look something like this. So say this is this row, but you have an additional row at the bottom. These would be all zeros right down here, okay? And then number two, it has leading ones for all the rows. So as you can see here, leading ones. Leading one, leading one, leading one. On top of each step of the staircase, essentially. And then third definition, and then three. Let's see. Every following leading one is to the right of the previous leading one. Again, this is so subconscious that I kind of almost forgot about that. But it is true that each leading one is well to the right. But well, let me just make sure I'm not doing something ridiculous here. So yeah, I kind of did an example of Gaussian elimination already. Oh, I'm in a slight risk. Oh, sorry, that's completely off topic. No phones in class, guys. Promise, I'm just... Guys, no phones in class. Okay, kidding. Am I even live? That would be so funny if I wasn't. I spelled my own name wrong. I am live. This is so funny to me. But yeah, I'm in a Slayers. That's so cool. Anyways. So, moreover, we say A is... Furthermore, we say A is an reduced row echelon form if if and is, okay, that's redundant. If the following, there's criteria for which all these criteria apply to row echelon form. This fourth criteria determines if it's reduced row echelon form. Each leading one is the only what does that say? I can't read. Earn non-zero entry. In each column. All right. So that's kind of the gist of that. So this right here is row echelon form. But what would be an example of reduced row echelon form? So one example, let's do a simple 2 by 2 matrix. You have these two 0 rows here. You have this, and then you have whatever number is left. This, by definition, technically is reduced row echelon form. But another example is what apparently it's this as well, but wait a sec. You have, well, this kind of unevenish staircase here. What's going on with that? Well, what's going on with my, okay. Wait, this is not reduced row echelon form. Okay, wait, hold up. Neither of these are reduced row. Hold up. I might have did a stupid here. See, you can tell I barely understand this myself. Okay, so these fall in matrix. So I was right about the first one actually. So this is reduced row echelon form, but this is also reduced row echelon form. So again, first column remains the same. Okay, I think I get it ish. So yeah, each one pivot needs to have zeros around it. So for example, this one right here needs to have a 0 afterwards in this column. Same with this, and then this is just gonna be whatever it wants to be because we have 0 at bottom. But say, what is going on with this, however? That is interesting. But yeah, every matrix can be brought to reduced row echelon form in elementary row operations. I'm not going to torture you with a too complicated example because Lord knows I can't deal with that. I don't have the stamina for that, and I really want to move on to add the bottom if the bottom row is all zeros or not. That's inconsequential. But yeah, eventually you don't. Again, I don't know what's going on with this. Because wouldn't this be 1 and this be 2? Why would it not be that case? No, one's on top. Then this one. Okay, wait, hold up. Okay, I do need to really think about study this and go over this a little bit more maybe. Again, I'm not gonna do like an example where I just like row reduce and like brute force it? Because I can do that on my own time and study for it. And I already know how to. We're gonna do more row reduction anyways when we get to inverse matrices anyways. So I can practice it then a little bit more. So but yeah, reduced row echelon form is actually really cool, however, because once you have like say an augmenting matrix like this, you can simply x1 plus x2. I'm just gonna make up stuff, and then x3 equals 4, x4 equals 5. And then you can also parameterize theoretically form S and T x, and they're arbitrary, but is that next section? I think that's next section actually. Oh no, that's not. Okay. Okay. Maybe I should practice this a little bit actually. Okay. We can do this. I'm sorry, this was so long ago to me, it's kind of foreign at this point. We're gonna do one. We're doing one reduced row echelon form example, and then we're gonna move on, okay? Just as long as I hit each of the bases with this. Because keep in mind, this course only gets more and more abstract as it goes along. You get, or this is not in calculus, algebra technically. But again, this is like the traditional math and like more physicsy based math. This is about the closest you're gonna get in this entire course. It gets so much more abstract from here, and it gets a lot more challenging because of that. And I don't like it, but you know. So let's say we have a system of equations. Let's just use the x, y, and z like I can't write a z like so. So just gonna use that simple equation. So let's try 4x1 minus 3x minus 3y, and let's set that equal to 9. Thought I was gonna do something fancy there, but no. And then let's do let's not do it that easy. Let's not make it too easy. Okay, and well, let's do 12x minus 4y plus 9z, and let's set it equal to just 1. Again, there's also a chance that some of these equations might just straight up not have a solution, but you know, we don't have to worry about that right now, right? I realized I subconsciously did 9 and 5 twice. Okay. So let's quickly row reduce this. R3 equals 3R1. What else? 2 minus 1/4 R1. So that gives us 0 for these. Let's not give us 0 for that, however. That's okay. So minus 4 minus 1/2 gives us minus. Yep. And then, so this is the same, by the way. This, don't have to worry about this for now. Okay, this is also the same because you're just subtracting by. Oh wait, no, my bad. This is the same because you're just subtracting. No. Okay, this is the same because you're just subtracting by 0, which gives you nothing. Same with this. This is also the same, so it does make my job a little bit easier. And then yeah, maybe I made this a bit too tedious. Oh, it's already 1. Are you guys fine if I just move on? Because I really need to get to the more complicated stuff of this course. And if I dilly-dally with Gaussian elimination, we're not going to really get anywhere too far. We can do more Gaussian elimination when we get to a matrix algebra anyways. So these are the simple definitions that you need to know. Take a screenshot, a picture of this, and because I can do this, it's tedious, takes a while, and no one wants to do it. So 0, you know. Something like this. And then this has to become, yeah. This is the generalish definition of it, hopefully. Unless I got it completely wrong, then I'm giving someone a heart attack right now, probably. Actually, to make it simpler. Yeah, okay. And then these can be whatever they want to be. Yeah, okay, perfect. Alright. So, and again, reduced row echelon form was important earlier in the course. It's cumulative, so it might pop up on the test. But you can really solve a system realistically with row echelon form. It might take a little bit longer, but you can work out examples. You get something. You can eventually get something like. You get something. Wait, hold on. Eventually, if you okay, hold on. I'm gonna do like one final part of the Gaussian elimination. I'm gonna move on because I feel like this part's important at least. Because this part definitely returns back later in the course. So if you fully reduce something down to say, let's say, oh wait, you know what? I did forget the rank. So I'm just gonna define the rank real quick. So the rank of definition. Let's do a definition. Rank of a matrix is okay, if I remember it's the wait, hold on. Am I being dumb? Oh my gosh, bro, these early stuff. Can we move on to eigenvalues already? Anyways, I'm struggling with this. Okay, let me just clarify because this is definitely going to show up. I thought the rank was just the amount of like leading ones you have in a row reduced matrix. But if it's not that, then we have a problem. So in general, a matrix A will have more than one row echelon form. Or you can show that one row echelon form of A is unique. Number and position of leading ones. So definition, let A be the B matrix row echelon form neuron of A. To find the rank as. Okay, yeah. Okay, yeah. Rank of a matrix is just the number of leading ones in a row reduced or just a reduced row or just in a row echelon matrix. So you don't have to fully do reduced, right? Just put in row echelon form for these. So for the example, the matrix this, this is an important matrix. It's going to come up later. Hey, hello identity matrix. Everyone say hello identity matrix. Identity matrix is so cool. There's going to be a lot important later, but you just hear now because I can't think of any other better example. But yeah, the identity matrix has 3 leading ones. And you can kind of like see it as a staircase, even as staircases. So that's what. So set this matrix equal to A. So then you can do a rank of A like this, like a rank operation of A. So rank of A equals 3. And another example, before I move on, let's try to do a row reduced example. Is that a row reduced example? I can't tell. But let's see. Number of leading ones here. Actually, hold up. Number of leading ones here. Well, that's 2. You have this, you have this. So, despite this having the same amount of rows as this, it has a lower rank. Let's say this B. A is already taken. So the rank of B, despite having more rows and columns, is only 2. How about that? So yeah, this definition isn't that hard. I thought it was confusing. No, it's not. But yeah, there's also a case. So what else I was trying to get at before I got caught up in the rank stuff is there's another thing I gotta remember. And is that if you say, let's kind of do a fully row reduced example. Like a system of a linear consists of the rank, then okay, I'll worry about that later. Let's say you have a system. Okay, I'm just gonna steal this example because I can't think of anything better. So wait, hold on. Is this system in reduced row echelon form? It should be. Okay, yeah, it is. All right. So let's say you have a system like this. So something like this. Something like that. Again, I want to move on to something important. What do you notice about this? Well, z is a free variable. You can't really necessarily solve for z without making things too complicated. So what we do in this case is that we parameterize z and say z equals t, and then we also clarify t is arbitrary, which means t can equal whatever it wants. It can equal 0, 69, 1 million, who cares? You don't necessarily have to solve for it. So if we say that z is this, we can plug z equals t, we can plug that in. So we can get am I doing this right? Maybe not. And then we can just like say x is equal to minus 2y plus t plus a, right? Oh no, you're not. No, you're not supposed to do that. Wait, that is no. You should not do what I just did. That's really bad. That was really bad. Okay, wait, hold up. Okay, yeah, you have to substitute the t back in, and then you solve. Okay, yeah. Solve for y here, plug it back into here, and then solve for x, and then you say the solutions will eventually be so. And again, another parameter you can use is also s. You can use other parameters as well, such as u and v, especially when discussing vectors and stuff. But in general, when it comes to parameterization, the two most common variables are going to be s and t. So, but again, as long as you specify that, well, whatever parameter you decided to use is arbitrary, and that you didn't choose a parameter that's already taken. Like, say if I say x is arbitrary, then no, you can't do that. But yeah, that's kind of a very general thing in math, is that you don't want multiple things of the same variable, right? Because then you're just going to get incoherent nonsense, essentially. And you don't want that. No one wants. No one wants that. But yeah, so these are the solutions if I were to algebraically go for it, but we don't have enough time for that, and there's bigger fish to fry. So that took way longer than it should have. Let's get a bit of a move on here. Let's get a little bit faster, all right? So section 1.3 is basically just basic vectors. So kind of the basic vector notation is essentially just a matrix column. So you have x1, x2, xk, or xn. Either works. You can also do the same thing with y. So something like that. Doesn't matter. But yeah, the same thing goes, say if I want to add these two vectors together. Oh, guys, it's going to be so groundbreaking. What am I going to get? I want you guys to guess. What am I going to get? Oh, wow. Am I going to get this? Wow, it's so groundbreaking. And I can do the same thing with a scalar multiple. I can do the same thing with the scalar multiple, and then I just get, oh, I realize, probably not a good scalar multiple. And I get, well, the same thing. Wow, kx1, kx2, kxn. Something like that. Yeah. Yeah, it's just kind of the basic thing. And you can use that well-defined basic solutions. So let me just like write out a problem. I'm not gonna solve it, but I'm just gonna write it out to like kind of give like a system of equations. It's gonna be kind of sound counterintuitive because I earlier did reduce these types of system of equations, but let's say you want to make a linear combination. So let's say V is a linear combo of V1 and V2. Well, what do you get? Let's say V1 equals V2 equals. Well, then how do you do a linear combination? You just write it out like this, basically. Essentially something like this, right? Right, does that make sense? I should make... Oh wait, hold up. I almost did a thing. I almost did it really bad. And then you set that equal to, well, my u vector, which is that. And then once you do that, you get a system of equations. So that becomes a1 plus 4a2 minus a2, a1 plus 3a2. Oh wait, no, excuse me. Should not do that. 7, 5 minus 3. A1 equals 10. Oh wait, no, that's mine. I almost gave myself a heart attack. But yeah, see, we already have A1 and A2, so I can theoretically solve this. Well, actually, no, the system. Okay, that was. I realized because then the solution to the system would have literally just been this, and well, it just kind of defeats the purpose of the whole thing, doesn't it? So, and then your goal is to solve for this system, find these, and then basically just turn them into, well, initially it was these two, so let me just kind of do the initial. And then eventually this would turn into, well, 10, right? Yeah, 10, and then minus 7, 4, minus 1, 3, 0, and then it equals 5, 7, minus 3, 10. So, yeah, it's pretty simple. My handwriting's bad. I'm sorry about that. Just another theorem. Okay, hold on. If x1 to xn are solutions to a homogeneous system of equations, a homogeneous system of linear equations, and any linear combination of x is a solution of the system. So yeah, say if we have. Okay, so just a brief theorem. Let me erase this. Brief theorem time is not that important, but it's just like a good to know type thing. So brief theorem. So say if, for example, so if x1, xn are solutions to a homogeneous I don't know if I spelled that right. System of linear system. So then, essentially, what this is saying is that, well, if this is homogeneously correct, you can essentially make it so that any any linear combinations. So we have this, and then this, and that would mean something like this is a t, by the way, would equal 4x plus ty, 4x and plus tyn. Something like that. Something like that. Okay. So, yeah, and then t is just arbitrary. I don't know why bro used t as a. Again, I'm not copying directly off the same thing. I do change numbers and stuff. But, yeah. I prefer c as a variable here, actually. For c as a number, obviously. Thankfully, we don't do complex numbers. And that would. I don't even want to think about that. Don't give them ideas. So, yeah, there's some practices too. But now we're finally going to move on to chapter 2, which, yeah. Matrix and transposes. Matrix addition. So, scalar multiplication and transposition. I'd say transposition is the easiest part. So let's do a quick theorem. Real quick, however. So let's say A equals matrix Aij, or B equals Bij. I and J are rows and columns, by the way. So if they have the same rows and columns, and these two matrices are equal, hold on, let me see. So wait. Then Aij equals a Bij for all I and J. Okay, something like that. And then you see that. So yeah, for any rows and columns, they're equal. Okay, that makes sense. I was overthinking it. So yeah. Okay, sorry. Yeah, okay, that's kind of the simple thing. But now we can use this theorem to our advantage. So this is going to be very simple, so we're not going to do much. I don't think I have to do much with this. I'm just going to, so let's see. So A Ij equals this for any value of Ij. Wow, that's so innovative. Okay. Let's do a quick simple problem. Let's do a 2 matrix. Let's do a 1 matrix, what do you get? You get 3. Let's do A and then B. What do you get? A plus B, A plus B, A plus B, A plus B. There. It's that simple. Yeah. I'm so smart. Wait, no, that's not. Did I mess up? Oh no, I'm good. Okay. I overthought things for a second. I was like, wait. Okay. Yeah, this principle is easy. Now let's move on to scalar multiplication. So, this is the next theorem. K A equals K A I J. Okay? Yeah, it's pretty simple. So let's say we have a 1 matrix and we want to multiply it by 2. What do we get? 2 times 1, 2 times 1, 2 times 1, 2 times 1. What's 2 times 1? It's a 2 matrix. Wow. I'm only using these like very elementary simple problems just to get by as fast as I can. And also some other theorems that go without saying. 1 times A is just A. 0 times A is just 0. Yeah, it's pretty simple. And yeah, there's some other stuff too. Again, these things like the closed-end addition stuff become much more important later on. But I feel like a lot of these are so elementary and arbitrary that they shouldn't be too complicated. Again, it gets a lot harder later, but I guess basics are important. And the last thing is, well, okay, the interesting thing, the transpose. So, this is where things start to get interesting, because the transpose, one of my favorite things about linear algebra. So, this is A of t of a matrix. A of t equals A, J of I. What? But nothing changed. No. See the I and the J order? They're flipped. So what does that mean? Best to do this with an L squared matrix. So let's do a 3 by 2. So A, B, C, D, F, G. I'm not going to use E because that's Euler's number. So yeah, I have 3 rows and 2 columns. But what happens when we take the transpose? Well, then you get it. So if you have 3 rows, 2 columns. Oh, guess what that becomes? That becomes 2 rows and 3 columns. This is very innovative and groundbreaking. Look at this. Okay. So what does that mean? You get A, B, C, D, Euler's number, F, G, like this. And again, that's interesting. I mean, it technically works for a square matrix. This is 2, right? But yeah. I also put clarification, just so everyone knows. What happens if you take the transpose of the transpose? It just gives you the original matrix. It's that simple. So yeah, transpose is kind of like just like rotating things around. Did I actually do that? I might have screwed this up actually. Oh yeah, we're supposed to rotate this clockwise. I kind of okay. Look, guys. I'm sorry. I'm sorry. Okay. So it's actually this. Yeah, that would have been really bad. I am. But yeah, it's essentially a way to look at that is that you just rotate it clockwise, 90 degrees, like this. And then that means that this top right thing, this top right number stays the same always. Right? Okay. I know I'm messing up on a lot of things. And again, the same things apply here. So transpose of A of t multiplied by scalar, same thing. And then A of t plus b. And no, this becomes this. I know it makes algebra kids cringe sometimes when they see something like this because it gives them flashbacks to other horrible things. But these are matrices, okay? These are not fixed scalar numbers or variables. These are matrices, all right? Just don't think about doing this with like not transpose, then you're fine, okay? Transpose is fine. All right. Again, these examples that I can work out later, I can just like my idea is to like refer to these back later. You know, right? So let's do some vector multiplication now. So let's say we have a vector of x. So this is our vector goes to n, like so. Is there another theorem? I think there's another. I could use some water. Give me a second here. Let's take a water break, actually. Could use some water. Again, this gets so much more complicated so fast. We've been going for an hour 30 now. I could really use some coffee, but that's okay. Yeah, let me see the. Also, I could get kicked out of this room eventually, which would not be very good. Let me. Oh. Okay. Checking the date one outlook. Is it? Okay, yeah, no. This is probably for wind, right? Inhale, maybe. Yeah, okay, it's for hail too. Typical. Nothing ever happens, anyways. Okay, what was I talking about again? All right, matrix vector multiplication. So you denote. Let R be the set of all real numbers. We denote Rn by the set of all n multiple of real numbers. So I like to see Rn, this Rn, as kind of the dimension of things. Rn. So like for example, R2, 2-dimension, 2 vectors, R3, 3-dimension, 3 vectors, and so on, right? Does that make a little bit of sense? So yeah, linear combination of x and y and x of t of r vector equations. And then, oh. Okay. Let me do an example. Again, the examples are literally written right in front of me. Maybe this might not be the most effective way at studying. But, you know, I don't remember doing this, maybe because I wasn't in class that day, but this is good. So let's do A, B of C of A prime, B prime, C prime. So just and then let's have a B vector that equal D prime. Again, these aren't derivatives or anything. These are just like, wait, are they derivatives? Wait, hold on, I'm stupid. Are these derivatives? It doesn't matter. Okay, wait, hold on. This is the OG system of equations. Wait, dude, this is gonna be my new phrase. Am I doing this right? And then, okay. So you write it to this, and guess what? You turn it into a bunch of vectors. Yeah. Oh, wait, no. Wait, no, yeah. I can also just rewrite this as well. B vector. Yeah, so simple. Again, these topics come up later, but more complicated. So maybe let's just try doing their beefy, more complicated version and just like skim through this part because these parts are really inconsequential. They're more like, for example, so we have matrix vector multiplication. Now we're going to do matrix multiplication, which I feel like we already did. But maybe there's something I'm missing. Oh, yeah, okay. I wouldn't say these are matrix multiplications, more like matrix composites. Okay, yeah, because if you have some, okay. So yeah, let's say, for example, you have something like, well, S of T of X, that actually becomes X of T of X. Wow, very informative. Something you probably learned in your algebra class. But yeah, you can kind of use this for any matrix. This theorem, like for example, you have T of A dotted T of B a vector. Same thing applies. T of A with T of B X, something like that. Yeah, pretty simple. Nothing too crazy. But wait, you can also. But the transforms. Wait, that equals A of B of X inverse. Wait, hold on. So next, no, it's an arrow. Right. Okay. Yeah, that because these are transforms, right? So. Okay, wait. Okay. Wait, hold on. The theorem. I missed the theorem. Let me write this theorem down real quick. I think this is important, maybe. So, if transform of A is of goes from R n to r of n, transform, and transform of b is also the same thing. So it's r of n to r of n, right? Because you can't work this stuff in like weird dimensions, right? Right. Wait, r of p to r of n? What? Wait, so the... Wait, hold on. Okay, this is weird. I might have screwed something up. I don't know what it is. Is there something I'm not getting? Can I understand when you're multiplying the same size of a matrix, but when you're doing something like this, I'm a bit baffled by this. Again, I want to move on to like kernel and image space stuff, but like this is not clicking. And if this is not clicking, then whatever's down the road could very well not click either. I don't know, man. I hope this isn't cumulative. Okay, I need to at least know how to multiply out these matrices. So how do I multiply matrices of two different sizes? What? Okay, hold up. How to multiply matrices with different dimensions. Different dimensions, I mean. So. Okay, wait, yeah, okay. Hold up. So let's say we have a matrix of, well, 1 minus 3, 5, 4, minus 2, and 1. And then we multiply it by 6, 7, 4 minus 1, 3, and 0. What you want to do is you want to multiply this first row by this column, right? Right. Also, keep in mind, these two matrices are not cumulative, meaning these are going to give you two different answers. But just a quick clarification, if anyone needs that. Okay, I'm like a visual learner. So, I gotta take notes. So this has 3 cols, 2 rows. And then this has 3 rows, 2 cols. So then our resulting matrix should have this, right? Right. I think so. Right? I don't see why not. Okay, that's 2 cols, 3 cols, 2 cols. No, that has 3 cols. Wait. There's something I'm not getting here. But I'm getting really tired and I might get kicked out soon, so I might have to resume this. But it's good I'm finding stuff that I'm doing wrong, right? Because like I was willing to stay up for this, but now that there's a slight risk and also some stuff I need to attend to in the morning, it's not the best idea anymore. But that also means I'm missing out on the most valuable things, in my opinion. But I also need to okay. Cause I completely forget how to do this? I probably did. Okay, there's tutorials on this. I might have to go to bed. I'm actually getting really tired and fatigued. I don't wanna. Because the idea was for me to study like the later stuff and like. Okay, I'm gonna finish this up tomorrow. I'm gonna review what I need to, and then I think it's better if I start with chapter 3 because I feel like chapter 3 could have the better information ish. Yeah. Okay. Wait, no, we have linear transformations in elementary matrices, so. Again, it's a very noticeable knowledge. Okay, I'll finish up chapter 2 actually. So I can get to chapter 3 eventually. But it's like at least if I stay up on Saturday, I have nothing. Um, and I have a chance to do that. Okay. Okay, wait. So 1, 6 plus 5, 4 plus 3, -2, right? So this would be a 2 by 1 matrix, then, right? And then I multiply this and this, so that becomes -3, 7 minus +4 -1 plus 0, so I don't have to worry about that. And that becomes 26 minus 14, 21 minus 4, which becomes 17. 26 minus 14, 26 minus 4. 12, 17? Oh, I do not know. Um, no, that's probably wrong. Actually, that's probably wrong. That's definitely wrong. Okay, wait, hold on a second. Because, like, when I multiply by vectors, it's simple. Because, like, all I need to do is, well. Okay, wait. So, it should be. Okay, cool. It should be based off of, well. Did I make it happen by the library people? So this is 3 cols, 2 rows. This is 2 rows. No, this is 3 rows. No, this is 3 cols, 2 rows. This is 3 rows, 2 cols. Okay, not making sense. So this should be 2 by 2, right? Because this is the same, this is the same. Oh no. Or would it be 3 by? No, what? Okay, I'm confusing myself. I'm confusing myself more than I have to. I'm genuinely lost on this. Good review question though. Oh no, it should be 2 by 2. Okay. But why? Twelve plus 21 is not 36. Oh wait, no. Okay. I think I'll come back to this. We'll review. I'll ask questions about this to my professor tomorrow. Then we'll review this, and then we'll move on to chapter 3 afterwards tomorrow. Okay. Because, yeah, I wanted to do this tonight, but I don't think I can. But these next concepts are going to be much easier, okay? I don't even think I have to do this one real quick. But, that's it. First of all, remember I said earlier, identity matrix. So what is the identity matrix? Well, it's essentially a fully diagonalizable or diagonal matrix with the eigenvectors as 1. That's the kind of base definition of it. You don't have to know the about eigenvectors to really know what an identity matrix is. But generally what an identity matrix is, it's a square matrix and it's an identity matrix with the eigenvalues of 1. So this is the identity matrix in R3, and this is what it looks like in R2. Wait, this is bad. I wrote R3, and R4 is just yeah. You get the idea eventually. I mean, not eventually. It's pretty simple. But how do you solve for an inverse of the matrix? So let's say A is, again, some samples use just letters. I don't like using that. I'm going to make this easier on myself, actually. Because I want to go to bed soon. So this is A. Now, how do we find A inverse? Well, you set A equal to the identity because, well, A times B gives you the identity. Normally, yeah. Okay, yeah. And also another thing about the identity matrix is that any matrix times the identity matrix just like yields out the same matrix. That's how it works. But yeah, okay. Just anyway, so you can make this an augmented matrix now. So it's 5, 0, 0, 6, 5, 1, negative 3, 1, 8. I realize how much of a pain I made this to solve for myself, but that's okay. And now we solve. So let's just do 1/5 R1. So that becomes 1 6 over 5 minus 3 over 5. Okay, the idea is that, okay, hold on, I need to clarify. The idea is that this, we want to reduce this down to this, and then this right here is going to be our A inverse, okay? That's the idea of it. So we kind of don't really care what happens here until we get the identity here. So that's the goal, which is essentially reducing this to row echelon form. Because square matrix of that is not reduced row echelon form, by the way, just row echelon form. So that's just 1/5, 0, 0, 5, 1, 5, 0, 5, 1, 0, 1, 0, 0, 0, 1, 0, 1, 8. That is not an 8. I don't know what that is not an 8 either. My handwriting is getting worse as this goes on. Da, 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 da. Okay, next up we have R3 minus 1/5 R2. 0, 0. Wait, no, that's not. Oh wait, yeah, it is. 1/5 of 1/5 of 1. Wait, no, this is 1/5. When might it be? 10 to the 5 squared, so that'd be 40 over 5 minus 5 over 5 minus 1 over 5. So that'd be 39 over 5. Not the best thing in the world, but it's not 1/5, 0, 0, 0, 1, 0. 0. Yeah, okay, just back to my. So that becomes negative 1/5, negative 1/5. This would stay. 0, 5, 1, 1, 6, 5, negative 3/5. Right, okay. And now all we have left to do to fully reduce this. Again, there's a chance I might have gotten something wrong with this. Because this is a complicated step. Surprisingly, this wasn't actually as bad as I was expecting initially, though. Not ideal. So now we just need this one and this one. And oh wait, we need all these to be 0, I just realized. So now we can't make these all 1 yet. Oh no, okay. How do we make this 1 0? I guess. Okay. Because this would not. Again, I realized that we put. I contradicted myself because I said it basically putting it in the row echelon form, but if I put this in the row echelon form, it does not make the identity matrix right away. So I have to 3/5, 39/5. I'm gonna make this 0. R1 minus. Oh gosh. Okay, normally it won't be this hard, so you know what? I think it's fine if I leave it there. This was not supposed to be hard. Like, really, once. Like, yeah, there's easier examples out there. This is too awkward. Okay, 2 more, and then I'm done. Just 2 more theorems in general. And then, so an elementary matrix is kind of what we've been doing, but we, like, need to describe, like, what the matrix elementary operation is. Hence why it's called matrix elementary matrix. So this is going to be pretty simple. So when you're reducing into when you're so yeah, there's a proof. Don't have to worry about that though. So let's say we're reducing something, and then like, so you're row reducing this matrix A, and it equals 1 minus 2, 3, 0, 4, 1, 6, 5 minus 3, and you're row reducing it. I say first thing you want to do is subtract R3 minus 3R1. Well, what that gives you is you get an elementary matrix of this. And the elementary matrix of this is this row operation done on the identity matrix. Can you have? Yeah. Okay, no. This can only. This only applies to This does not apply to, like, say, in I of j, where I equals 4, and then j equals 69, 420. That is not 420. 420. See, this just wouldn't work because it's not a square matrix. Square matrix essentially is just AI of j, I equals j. It's that simple. Okay? But yeah, all square matrices are just operations on the identity matrix. So identity matrix 0, 0, 0. And then the third row minus 3, so that just be this. And that's our first elementary matrix. And eventually the idea is that you're just gonna keep row reducing it until you multiply all these elementary operations together to get your full elementary matrix. Luckily, multiplying elementary matrices is a lot easier than whatever the heck I was trying to do, so. But yeah, sometimes you have to, like, say, find A1, and then write A as your product of elementary matrices, right? That makes sense. So yeah, it's not that hard, especially compared to the next topic, or last topic of the night, which is, well, linear transformations. And the sad part is that it comes back. It comes back in chapter 7. No, it comes back in chapter 9 with a vengeance, and it's just so much more nasty in chapter 9. As if it's already not nasty enough in chapter 2. But that's okay. It's not, but it's okay. So, transformation matrix is simply transformation from, well, the R of n plane, or the R and set to the R of m set. So it's kind of like a projection in a way. You can project 2D objects into 3D. You can project 3D objects in 2D. But yeah, you also need to test if something's a transformation. So this is our first, like, definition. Is it a transformation? And it's a transformation if the following are true. Number 1, the transformation is closed under addition. So for example, you have transformation of x plus y, and then it equals the same as transformation of x plus transformation of y. That is the same. That's the criteria 1. Criteria 2 is if it has a scalar multiple. So let's say you have transformation c of x, and then you can factor that out for c's in the set of real numbers. You don't have to worry about this, by the way. I just think it's just, like, good practice to acknowledge. But it's not the end of the world if you don't put that. But that just becomes c t of x. And that's also the same. Okay? So that's how you tell if a transformation is linear. And it's for all vectors x of y in R, the set of real numbers. It's in power of its dimension, right? So I feel like doing at least one transformation example is important, considering I wasn't able to do an inverse one. Again, a lot of these practices I plan on doing on my own time, but I feel like doing an example here is for a transformation important, considering well, so suppose that T is a transformation from R of 3 to R of 2. We're going from Fat Big Paper Mario. We're going from Fat Big Mario to Paper Mario. Okay? So, T is the transformation of 1, 0, 1. And it transforms to 4. And this is our first transformation. And then T, next one is T, transformation from 0 to minus 3. And then that equals 0, 1. Now I wonder when canvas is going to come back up. Do you ever think of that? But you need to find the image of T of, of the following. So you have 3 minus 4, 9 under T. Right under T. So how do you find that image? Well, I want to express it as a linear combination. So keep in mind that this is a 3D vector. So you want this vector to be set equal to A 101, this 3D vector, A1, A2, right? I just need to clarify. Oh wait, no. What? No, you already have set numbers. Hold up. It's 2 and 4. So this is 2, this is 4. So you confirm that this 0, 2, minus 3. Like that. Wait, 3 minus 2? Why would it be 3 minus 2? I'm getting so tired, bro. So yeah, it's a linear combination of 101 and 3. Oh, I forgot you have 2 rotational. Okay. I think for the sake of my stamina and the fact that I have stuff in the morning, I have to cut it here. I wish I could continue, but truthfully, I physically cannot. Maybe a good way to be to work backwards, kind of. Because I really need sleep. Not because I can go for like maybe another hour or two, but I have stuff in the morning. And there's actually stuff happening tomorrow that I was not aware of until now. So there's just a lot more important things. Unfortunately, I have to cut it here. But I'll be back tomorrow around no, not same time, earlier time, like 8, 9 Central. And hopefully work through all of this as far as I can. And we'll backtrack a little bit through chapter 2. We covered like the stuff that I'm more iffy with in chapter 2. And then hopefully build up. Because I will say the rest of the chapters aren't as long. They're more abstract. But yeah, chapter 2 by far is the longest chapter. But they have more abstract ideas here.
I will say also some of these come back like transformations, like linear transformations, and rank and inverses too. So yeah, I think that's good for now. See you tomorrow at 8, or not tomorrow, later today at 8 Central, I guess. All right.